Hi, this is Sir Aris. Let us talk on exact equations and integrating factors. To begin with this discussion, let's start with an example. We solve the differential equation 2x plus y squared plus 2xy y prime. Um, so to solve this, take note that this equation is um, it's not separable nor linear. However, we observe that a function psi of x and y equal to um, x squared plus xy squared, we can write partial derivative of psi xy with respect to x as 2x plus y squared, and also partial derivative of psi with respect to y is equal to um, x 2xy. Okay, in this way we can write the differential equation as um, partial derivative of psi with respect to x plus partial derivative of psi with respect to y times the ordinary derivative dy by dx. If we assume that um, y is a function of x only, then this means that if we use chain rule, you have d psi by dx, which so psi is a function of x and y. This is d by dx of x squared plus xy. We write it as 2x plus um, hold on, this is x y squared. So this is y squared plus, take the derivative with respect to here with respect to y, that would be 2xy dy by dx. Okay, and this is 0, so you have the psi by dx equals 0. That means that psi xy, which is equal to our x squared plus xy squared, is equal to an arbitrary constant c. Okay, arbitrary constant. So this is our solution written implicitly. So we write here, if you want to write y in terms of x, you just have to rearrange. Okay, the key step to solve that example is on finding that function psi, so that if you have functions m and n, it satisfies partial derivative of psi with respect to x equals m, partial derivative of psi with respect to y equals n. And for y, a function of x, we have this expression given by d by dx of psi. And this differential equation can be written as derivative with respect to x of psi. So we can solve psi exactly. And this equation written like this is said to be exact. We use to make an organized method in solving problems like this. We will make use of uh, we are making use of this theorem, where if you have functions mn, my, and nx, where subscripts denote partial derivatives, that means you have if you have um, my, that means partial derivative of m with respect to y. And if you have nx, that means partial derivative of n with respect to x. Okay. Continuous in a rectangle with center xy. You have this exact differential equation if and only if you have these conditions. Partial derivative of m with respect to y equals partial derivative of n with respect to x um, at each point in the rectangle. So this also means that there is a function psi satisfying the exact differential equation, or the solution of our exact differential equation um, satisfies partial derivative of psi with respect to x equals m, and partial derivative of psi with respect to y equals n, if and only if m and n satisfy 2.7. Okay, so to prove this, our goal is so here you have this expression 2.2 is exact. So we want to prove that there's an exact differential, this is an exact differential equation if and only if. So you have a double implication. It doesn't only go one way but also goes back. That is the meaning of if and only if. Um, equation 2.7 is satisfied. Okay, it's easy to show that from 2.7, 2.2 is exact. How do you do that? So let's prove that 2.7 implies that 2.2 is exact. It means, so if it's exact, it means that there exists a psi. So there exists a psi such that uh, d psi by dx equals 0. Okay, so that's the meaning of our exact differential equation. So we start from 2.7. Okay, and so from 2.7, if we use these relations here, okay, given suppose we want to know that this psi here exists, so and it follows 2.8. Okay, so this 2.7 to be proven exact is the same as proving that 2.7 satisfies 2.8, this here. Okay, now if you take partial derivative of my with respect to x, okay, or let me start with 2.8. Okay, so starting with 2.7, actually I'm starting with 2.8, so let me remove this part here. So I start with this 2.8. um, Partial derivative of psi x with respect to y. This is equal to partial derivative of y, partial derivative of m with respect to y. Or let me also do the same thing for psi y. We take partial derivative of x of psi y with respect to x. That's partial derivative of x with respect to n. Okay. Um, Here, there's this partial, or psi x can be written as partial y psi, a partial derivative of x of psi with respect to x, okay, or that's partial y, partial of m with respect to y. Here, similarly, we can write partial derivative of x, partial derivative of y, psi. Okay, now these two here, this and this are actually the same because the partial derivatives commute. So this mx, my is equal to nx. Okay, so actually I think I've used a different direction here. I'm using 2.8 to show that here I'm actually using 2.2 is exact, implies that 2.7. Okay, so I'm proving first that if 2.2 is exact, that is there's a psi, then we show 2.7. So our next step is, given 2.7, we find psi. Okay, so next step, 2.7, we prove that it's exact. Okay, that is, we find psi. Okay, in the first part, we have psi, and then we prove 2.7, and we show that it satisfies 2.7. Here, we have 2.7, and then we show that there's a y. Okay, um, to do this, you first get, so our goal is to construct psi. Suppose we know that psi x is equal to mxy, okay, and psi y is equal to n xy. Okay, so assuming there's a psi satisfying this, okay, and we want to get that psi, if we keep y fixed, you have psi is derived by integrating psi x d x from x sub 0, no, from some variable, let me just exclude the variable here, from certain limits of integration. Okay, or we can write this as partial derivative of psi x, we know that as m, but it would be helpful to use different variables. Let's say I'll use here s and y ds. We start from x sub 0 to x plus hy, where hy is some function. Okay, simply we can write this as q xy plus hy. Again, this hy is an arbitrary function. Okay. Now, next step, we differentiate psi xy with respect to y. And that would be partial psi equals partial derivative of q xy with respect to y plus h prime y. Now we know that this partial derivative of psi with respect to y is nxy. So this is equal to nxy. Okay. Again, our goal here is to find psi. Now with this, we can get an expression for h prime y, that is nxy minus partial derivative of q with respect to y. Okay, now we can make sure that this h prime y is a function only of y. So to verify, so this is verify that h prime of y is a function of y only, we differentiate with respect to x. Okay, so if we differentiate partial derivative of h prime y with respect to x, we get nx and minus partial with respect to x of partial with respect to y q xy. Now remember, so this is nx, let me write that as simply as nx minus this. So partial derivatives can interchange. So partial y, partial of q with respect to x, that's actually our m over here. Okay, we take the derivative with respect to x, that's our m. Or this tells us that nx minus m. That should just be an equal sign. This is equal to nx minus m y. Now this nx minus my satisfies, that's our initial uh, condition here, my equals nx, which means that this is 0. So h prime y or hy is dependent only on y. So if we integrate, we get hy, uh, we get hy by integrating h prime of y. So that simply tells us that we can write psi, okay, after integrating m and integrating h prime of y, we get a value of psi. So psi, uh, so there exists a psi that can be solved exactly. So psi can be solved exactly. And that completes our proof. You have find a psi that satisfies those conditions. Okay. Now let's try to solve this differential equation. Here, this is our m and this is our n. Okay. If you take my, take partial derivative with respect to y, that's cosine of x plus 2x ey. Here, take partial derivative of n with respect to x, that would be cosine of x plus 2x ey. So m or my equals nx means that the equation is exact. So 2.9 is exact. Okay. So um, we have psi x equals m, which is our y cosine x plus 2x ey, and psi y equals n, which is our sine x plus x squared ey minus 1. We integrate psi x, you have psi equals, so integrate psi x with respect to x, that would give us y sine x plus x squared ey plus arbitrary function hy, which we need. Okay, now using psi y equals n, okay, or let me take psi y as partial derivative with respect to y of psi, which is this, we get sine of x plus x squared ey plus h prime of y. And this is equal to n. This is equal to n, where our n is sine x plus x squared ey minus 1. If we equate this sine x are equal, x squared ey and this are equal, so we get h prime y equals minus 1, which means that um, hy is equal to minus y. There is some constant plus arbitrary constant which doesn't matter. It will we don't need it. We can just use directly this hy equals minus y. Okay. So finally we can write psi as um, sine or y sine x plus x squared ey minus y. Okay, this hy here, and this gives us the solution. So since we have d psi over dx equals 0, then this y sine x plus x squared ey minus y equal to an arbitrary constant c. Written implicitly, this is the solution. There could be cases wherein you have uh, a differential equation that is not exact, but by multiplying it with an integrating factor, it will make it exact. Okay, so you have this differential equation, it's not exact. We multiply by mu. Uh, it would be exact if and only if mu my equals mu nx. So if we expand this, you have mu y m plus mu my equals mu x n plus mu nx. Or we can also uh, write it, or we can combine terms. Say um, you have mu y m minus mu x n plus mu my minus mu nx equals 0. Okay. Now this could be a very difficult task to look for mu. Let's have a simple case where mu is dependent on just one variable. Let's say is dependent only on x. In this case, mu y equals 0. So this mu y here, this becomes 0. Okay. Um, what we then have is that minus mu x n plus mu my minus nx equals 0. Or mu x equals mu my minus nx divided by n. Mu x is derivative of mu with respect to x. So this is, let me write it as my minus nx over n mu. Okay. If this condition, this expression here is dependent only on x, then we can find a mu that only depends on x also. Okay, so writing that explicitly, f my minus nx over n depends only on mu, then we can find mu that depends only on x. Okay, for example, you have this find the integrating factor of the equation 3xy plus y squared plus x squared plus xy y prime. If you take, this is our m, this is our n, you can see that this is not an exact differential equation. So if we write, if we want to solve for my and nx, my minus nx over n, okay, if this is dependent only on x, then we can find an integrating factor. Okay, so if you solve here for my, that would be 3x plus, actually, I think let me start with writing my and then x. Okay, my is written as 3x plus 2y, and nx is 2x plus y. Okay, now if we solve my minus nx over n, that would be my is 3x plus 2y minus 2x minus y over x squared plus xy. This would be, so this is 3x minus 2x, that's x. 2y minus y is y. This is, we factor out x, we have x plus y. This x plus y and x plus y cancel, so you have 1 over x dependent only on x. So we have to find mu, we get d mu by dx equals 1 over x times mu. Or you have d mu over mu equals dx over x. This means that ln of mu equals ln of x, or mu equals x. Now our differential equation becomes multiply both sides by x. You have 3 for x, 3. So we write mu m plus mu n y prime equals 0. You have 3xy plus y squared plus x squared plus xy y prime equals 0. Okay, this is now our new m. This is now our new n. Okay, so my, so m, let's write it as 3x squared y plus xy squared, and n as x cubed plus x squared y. We take mx, oh no, my, that would be 3x squared plus 2xy. We take nx, that is 3x squared plus 2xy. They are the same, so the differential equation is exact. Okay, now our next step, we find psi x. Okay, our psi x is our value for m, which is 3x squared. So psi x is m. 3x squared y plus xy squared. Okay, and psi y is x cubed plus x squared y. Okay, integrating psi x, we get psi equals, so we take the integral of psi x, that would be, so you have here x squared becomes x cubed over 3, so that's x3 divided by 3, 3 cancels, plus x squared over 2 y squared plus arbitrary function h y. Okay, and again this would be equal to, if we take partial derivative of psi with respect to y, that would give you x cubed plus x squared y plus h prime y. Okay, and this is equal to n. Okay, our n is right here, x squared or x cubed plus x squared y. So this are the same, this and this are the same, so h prime y. So this means that h prime y equals 0. So we can set h prime y or hy as some constant c, let's call it c prime, okay, or c1. So psi then can be written as x, uh, here are psi, this one, x cubed y plus x squared over 2 y squared plus c, okay, or c1. So from our exact differential equation, we have d psi dx equals 0. So this x cubed y plus x squared over 2 y squared plus c1 is equal to a constant c2. C2 minus c1, let's call that c. So we have x cubed y plus x squared over 2 y squared equals c. And that is the solution written implicitly.